In this part, I'm going to continue talking about network layer module, and the conversation will be about IP multicast. You already experienced packet delivery in unicast mode. So this was the project 1, this was project 2, but that's not all what network layer is designed for. Or in general, packet delivery is designed for. Specifically, there's also broadcast. We quickly introduced that, but we didn't actually use that enough, and this will be partially a subject of the project 2. And there's a concept of a multicast. Broadcast and multicast have kind of similarities between each other. It's just the broadcast is very simple mechanism. You just shout and hope somebody or everybody will hear. Multicast is trying to be a little bit smarter. It's still about shouting, but not to everybody in general, but rather specifically to specific groups of people. And as you can see on the slide, it's mentioned there is a forming of specific groups, maintaining of the groups, kind of leaving the groups, entering the groups, and so forth. So we're going to talk about this a little bit more in detail in later slides. Talking about the broadcast, there's technically two ways to implement broadcast multicast mechanism. So first of all, you can try to replicate stuff at the source. So this is what YouTube is doing when we're trying to broadcast the same movie in multiple clients. So then YouTube servers are basically replicating the same video and creating a TCP connections to individual users, and then users over those individual connections getting information. As you can see, it's not that efficient. Even if the same bits of data has been transferred across the network, they has to be transferred multiple times. I mean, today in YouTube case, it's actually not exactly the same bits because we're doing encryption on top of the HTTP, but in principle, it could be the same bits. So another way, and this is what done as part of the RTP protocol sometimes when we do like broadcast, is replication as part of the network. So like router receives the packet, or like switch receives the packet, it knows that it needs to replicate this packet into multiple directions, and then the packet has been replicated. So as you can see, if you do the same replication, kind of using in-network replication, like the same broadcast using the in-network replication, then you don't duplicate packets. So that's the obvious concept. However, there's a kind of, if you do in-network replication, there's actually two interesting elements. With broadcast implemented using in-network replication, you can actually also have multiple ways of doing business. So first one, you can use as blind flooding. And with this blind flooding or just flooding, you receive the packet and you kind of replicate this packet on all interfaces that you know about. That's simple, but it potentially can create the packet looping. So unless there is some mechanism to kill the packet, or like to stop packet being forwarded over and over again, if you do blind flooding or this just flooding, the packet will be kind of looped forever. And as part of the OSPF conversation, we actually talked about the controlled flooding. Controlled flooding is a quite simple idea. With one complication is you need to somehow decide which path actually be not used as part of the flooding. And in OSPF case, it was kind of random. Whoever received first, then it will not forward effectively. But in a little bit smarter way, you need to build some form of high-level logic to define which paths are being used, which paths are not being used. And for this purpose, what you can do is actually can build some form of a spanning tree. So kind of you pick the source, you do some form of computations, and then you created a tree, and over this tree you will forward back. So that's kind of the basic idea of the spanning tree and removing the paths from forwarding. However, there's also a complication which specific route of the tree to choose, because depending on which one you choose, you may have different properties of the network. So for example, if we happen to select node A as our source, then kind of source for the calculation of the spanning tree, then everything that was sent out by node A will be quite efficient. So it will go this direction, and this direction. So everything is quite fine. I'll just replicating what is shown on the figure. However, if we consider the same spanning tree, which was calculated from the perspective of node A that was picked initially, then if node D is sending traffic, then this traffic not necessarily will go the most optimal way. So for example, as you can see on the slide, it will go this way, this way, this way, this way. So instead of going like in some way over the optimal path between D, E, and F, because the spanning tree was calculated in completely different perspective, the packet will have to go a little bit further. It's not a major problem, just in case. It's just know that from kind of depending on how you build the spanning tree, you may have a different paths in the network. You're still gonna get all the nodes, maybe just a little bit more delay in some cases. So this is the good question of how to actually choose the route. There are multiple ways to construct the spanning tree. So one of them was a Dijkstra algorithm, for example, but under assumption that nodes already know the shortest path to everybody else. So for example, they already run in some form of routing protocol. The process can be actually much simpler. So for example, if we pick node E as our center of the network, I don't know, either we pick randomly or somebody provisioned it, then every other node can simply send a message over their shortest path, just basically towards the next hop, to reach the node E. And by the fact of sending this message, by the fact that this message was propagated towards E, it will build the spanning tree. So for example, if F sends packet to E over its shortest path, it will effectively mark this path as a shortest. And again, if node A is sending packet, it will create this as a part of the spanning tree, and so forth and so on. So for example, if C is somehow sending packet directly this way, then it will pick this path, and if node G is doing this way, then this part becomes the spanning tree. So then at this point, effectively the spanning tree is completed. And whenever any node in the system is trying to send multicast packet over this multicast tree, for example, node G is sending packet, then this packet will be effectively propagated along every edge of this tree. The actual IP multicast is a little bit even more complicated compared to controlled flooding, with respect that not every node in the system needs to receive this information. So for example, if node R in this case don't want to receive any packets destined to that specific multicast distribution, then it can simply send, or there's some mechanism to communicate that no packets needs to be received. So it can basically prune this branch of the spanning tree. And if the same happens to node R5, so for example R5 don't want to receive anything, then it will simply also have some mechanisms to prune this specific branch. And nodes that receive the packet, or nodes that have some idea behind that they need to receive this packet because there are some clients behind them that wants to receive this multicast packet, then they will keep this session going and will notify others using the mechanisms I will introduce next that then you want to receive this packet, and this branch will not be pruned effectively. Basically, compared with the controlled flooding, we have a mechanism where we can broadcast everywhere, we can do controlled flooding everywhere, and the places that don't want to receive information that we have controlled multicasting or controlled flooding, then they will explicitly tell us, oh, please stop to send packets to us. And so now we're done with the general description of sending packets to multiple destinations, and remember, we can do some form of a replication at the source when we basically sending the same packet towards different source address. We can do in-network duplication using broadcast, we can do network duplication using controlled flooding, and we can do network duplication using a multicast. Which basically trying to prune, in addition to controlled multicast, it's also trying to prune branches that basically don't want to receive this information. And now we're switching to a little bit more specifics to IP, and specifically to IPv4 multicast. And what happens in IPv4 multicast? There is a big class of IP addresses that reserved for so-called multicast groups. And multicast group is effectively an identifier of the stream of packets destined to one or multiple destinations, or actually zero or multiple destinations. And all the protocols that I'm going to be discussing, they're actually working using the concept of a multicast group. And kind of given this amount of IP addresses, we can have a lot of multicast groups. Just to give you a small note, multicast is not really available globally. So for example, if you're trying to create a multicast group to chat with your friends across like continents, this is actually not really possible. But we are using multicast in a little bit localized environments. So for example, for the IPTV, some form of IPTV are using multicast. Satellite networking are kind of very relying on multicast as well. And there are multiple other uses of multicast in kind of localized environments. In very small environments, IP multicast effectively works the same way as broadcast or controlled flooding, where you send a packet and this packet is kind of replicated by the switch to every host in the network. And if you have a little bit smarter switch, that switch will kind of also trying to do some form of a pruning. And if you heard ever a word IGMP snooping, so this is basically the mechanism on a switch level to do some form of pruning. But to implement it more than just for a single network, then we actually require a few more protocols. So specifically, we have two types of protocols technically. So one protocol, IGMP, is designed to work with the host specifically. It's like on the side of the host inside the network, and is designed simply to tell everybody in the network that I want to join a specific group, I'm still in the group, or I'm leaving the group. So that's kind of a point of IGMP protocol. The other type of the protocol, and there's actually many protocols, like including this multicast OSPF, DVMRP, PIM, and many others, that's simply trying to distribute information about that there's some hosts in that specific network are interested in receiving packets towards that multicast group. So it's basically all these guys, kind of, if I highlight those things, basically designed to distribute information about multicast group across the network, not just in a single IP network. And when I'm talking about the same network or the same IP network, I'm talking about the same Ethernet segment or the same Wi-Fi segment. To give you a few additional details, in IGMP case, the routers basically trying to query about memberships, or there's some form of a querying about who joined which group, and by who I mean which host joined any specific group, or if anybody joined anything. And with the multicast protocols, so those protocols effectively designed to build that spanning tree. And depending on the protocol, depending on the specific mechanisms they used, they basically built a different spanning trees. And there are different mechanisms, there's different amount of information they're storing, but I'm not going to be covering this part of this class because it's a much more complicated topic, even compared to BGP, OSPF, and RIP. And the only thing that I will mention is about IGMP, because it's actually a very interesting protocol. So effectively what happens is you may have multiple routers on the same network. And those routers effectively pick one of those routers as so-called querier. And this router simply sends a message to designated multicast group that everybody is supposed to be joined. Everybody who is speaking multicast, or like who is willing to speak multicast, they join this specific group 224001, and it sends the message basically asking which groups you joined. That's the kind of the nature of that message. And if anybody joined that group, it will reply. There's one tiny complication in this picture: the fact that reply not necessarily needs to be done by everybody. Because if you do everybody and you have inside the network, you have 200 or 300 hosts that join in kind of few specific groups, then it would be quite redundant for everybody to send that response. So what in IGMP host reply is trying to do is trying to optimize this mechanism. So as is highlighted on the slide, what happens is everybody who joined a specific group and they receive the membership request, they simply create some form of a timer. So from 0 to 10 seconds, they're simply waiting and like randomly picking a value. Then one of the guys, or several of the guys, will kind of finally time out, and they will send the message. Like basically, they will send a report saying, "Oh, I'm in this in such a group." And this message will be received by everybody, because that's the point of this 224001 multicast group. And as soon as some other members in the groups that was already reported in the message receive that message, they will simply suppress their own report. Basically, it's an optimization to avoid duplicated reports. Like if 15 guys join the group 224333, then only one of them technically needs to respond to the router query that if anybody is in the network, join this group. Because that's the job of the router, to simply know if anybody from the group is in the network or is available there, and if at least one guy is available, then router is happy, and it will basically report back using whatever DVMRP, OSPF, on some other protocols that this branch doesn't need to be pruned, and that's it. And for the living multicast group is effectively there is a special message that needs to be sent out by the node to kind of to indicate that it wants to leave the group. So it's just a little bit speed up compared to the process of just membership report. However, note there is one specific condition here. You don't want to report that you left the group if there are like 300 other people actually in that group already. So the condition that you will report that you left the group is when you actually sent out the membership report last. So if you were basically selected by using whatever random timers as a designated guy who's reporting about the membership group, then you will send out leave. And if somebody else still joined the group, if somebody else still in the group and will see the leave message, then it will immediately send out the membership report to prevent the kind of disruption of the service. There is still a small chance that the disruption of service will happen, but it's reasonably small and for a very, very short period of time. That was a short introduction to IP multicast, or kind of multicast in general. I talked about the broadcast, the flooding, controlled flooding, and multicast pruning. And specifically for the IP multicast, we talked about IPv4 multicast. So remember about the address ranges, remember about IGMP protocol that is used on the host side, like inside the one network, to do joining, to do maintenance using this query mechanism and kind of suppression of reports. There's leave messages, kind of to leave the specific multicast group. We have just remember that we have multiple different multicast routing protocols to basically build spanning trees, and the pruning mechanism is our kind of part of the those routing protocols to define which branches of that spanning tree needs to be cut out in order to save resources. Okay, so hope it was interesting, and see you next part.